Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. On February 1, 1922, parallel processing, or solving a million problems at once, entered into the realm of science fiction. But it was not until July 4, 1989, or 67 years later, that I discovered practical parallel processing. I discovered practical parallel processing as the vital technology that now underpins every supercomputer that is manufactured today. For 67 years, onward of 1922, parallel processing was the big and unanswered question of the field of computing. For 67 years, parallel processing was mocked and ridiculed as the beautiful theory that lacked an experimental confirmation. But on the 4th of July, 1989, parallel processing was upgraded from science fiction to supercomputer reality. That was the date that I discovered parallel processing and discovered it across a new internet that was a new global network of 64 binary thousand processors. That experimental discovery was the lockdown evidence that proved that the old paradigm of sequential supercomputing should be abandoned and replaced with the new paradigm of parallel supercomputing. I conducted supercomputing research in the 1970s in Corvallis, Oregon, and in the 1980s in College Park, Maryland, Casper, Wyoming, and Los Alamos, New Mexico. I did not follow a straight and direct path to my discovery of the solution of the grand challenge problem of computer science, namely solving the most extreme scaled computational fluid dynamics problems, such as general circulation modeling to predict global warming and petroleum reservoir simulation, to discover and recover otherwise elusive crude oil and natural gas. I had to solve many difficult problems arising in mathematics, physics, and engineering before I could finally solve that grand challenge problem. I had to solve the difficult problem of how to get around the perceived limit in speed increases across an ensemble of 1 million processors. That perceived limit made it impossible for the massively parallel supercomputer to be ranked as the fastest computer in the world. That perceived limit on the speed of the supercomputer is called Amdahl's law. That perceived limit was formulated by a supercomputer pioneer named Gene Amdahl. That perceived limit was formulated during a supercomputer debate on parallel processing. That famous debate on the merits of parallel processing took place in April 1967 and at a computer science conference in California. That debate was between Gene Amdahl, who was against parallel processing, and Daniel Slotnick, who championed parallel processing. Gene Amdahl won the debate, and the consensus thereafter was that parallel processing will forever remain a huge waste of everybody's time. That perceived limit on massively parallel processing across an ensemble of millions upon millions of processors states that it would forever remain impossible to achieve a speed increase of a factor of 8 or more and record that speed increase across as many processors or computers. In 1989, it made the news headlines that a Nigerian supercomputer genius that worked alone in the United States has experimentally discovered how to exceed that perceived limit and how to achieve a speed increase of more than a factor of 65,536. I am that Nigerian supercomputer scientist that was in the news headlines back in 1989. Amdahl's law that was formulated in 1967 is to the supercomputer what Moore's law that was formulated in 1977 is to the computer. Moore's law is the axiom that computer speeds doubles every 18 months. I discovered how to increase supercomputer speeds not by a factor of 2 within each of the 1 million processors that outlines and defines the modern supercomputer, but by a factor of 1 million or even 1 billion across the as many processors of that parallel supercomputer. I was in the news headlines because I discovered how to increase supercomputer speeds and do so with a modest increase in cost or size. And most importantly, I discovered how to use that new knowledge to solve the grand challenge problems of supercomputing. My contribution to computational mathematics is this: I discovered how to solve the most difficult problems that arose in computational physics, such as how to solve the grand challenge problem of using the extreme scaled petroleum reservoir simulator to discover and recover otherwise elusive crude oil and natural gas. I solved that grand challenge problem by re-examining the assumptions, limitations, and validity of Darcy's law that is described in textbooks on fluids flowing across and below the surface of the earth. Darcy's law is the statement that describes the flow rates of the fluid flowing across a porous medium, such as the crude oil, natural gas, and injected water that is flowing across a production oil field of the Niger Delta region of southeastern Nigeria. Darcy's law was discovered in 1856. Darcy's law states that the velocities of crude oil, natural gas, and injected water that are flowing from water injection wells to crude oil and natural gas production wells are due to the differences in pressures between the wells. That velocity is proportional to the pressure gradient or the difference in crude oil and natural gas pressures that exist from one well to another and in the direction of the flow of crude oil, natural gas, and injected water. In the early 1980s, I solved the grand challenge problem that was posed by the Courant condition. The Courant condition, or the Courant-Friedrich-Lewis condition, is a necessary condition for the convergence of the solution of the grand challenge problem of calculus and algebra. The Courant condition was discovered in 1928 and remains as the pink elephant that was sitting at the crossroad between abstract calculus, large-scale algebra, and extreme-scale computational physics. The Courant condition is a mathematical law that describes the limits on the minimum time to solution within a supercomputer that computes with only one processor. Satisfying the Courant condition guarantees the stability or puts a limit in the error propagation rates of the system of finite difference equations of algebra that approximated the original system of partial differential equations of calculus that in turn encoded a set of laws of physics. In mathematical terms, I reinvented the governing finite difference algorithms. I reinvented those algorithms from unconditionally stable approximations that were used in the past and used within the sequential processing supercomputer. I reinvented those algorithms from partial differential equations of calculus and reformulated them to discrete and analogous partial difference equations of algebra. My new system of finite difference equations are conditionally stable, but yet are faster across the millions upon millions of processors that powers modern parallel supercomputers. That mathematical invention, named the Emeagwali formula, was a precondition to my discovery of parallel processing. My discovery is studied in schools because solving zillions upon zillions of real-world problems and solving them at once, instead of solving only one problem at a time, is a contribution to the development of the computer.
Insightful and brilliant lecture.